In this episode of The Metabolomists, I am joined by Julie Courraud, who is currently a researcher at the Analytical Chemistry Laboratory of the University of Athens in Greece. When we spoke a few months ago, she was still working at the Department of Congenital Disorders of the State and Serum Institute in Copenhagen, Denmark, a place where she used dried blood spots collected from newborn screening to conduct research on several disorders. In our conversation, we discuss establishing new methods for metabolomic measurements, some of the pitfalls to avoid when planning a metabolomics project, and how samples collected in the clinics can help us further research. The Metabolomist is the podcast where scientists connect to explore the unspoken issues in metabolomics research. I am your host, Alice Limonciel, and together we will examine how metabolomic data interpretation is done. I will discuss with other metabolomists how they do this work, how they plan, execute, but also communicate metabolomics. Hello, Julie, and welcome on this podcast.
Hi, thank you for inviting me. I'm very happy to share whatever I can share.
Thanks. I'm going to start by saying a short bio about you, and then please fill in every missing information and correct me if I say anything wrong.
Sure.
You have a background in pharmacy and experience working in the clinics. You worked for several years at the Danish Center for Newborn Screening, where you used metabolomics for biomarker discovery in newborn screening, and also to study the impact of prenatal and perinatal events on health. This work is done primarily with mass spec-based methods applied to dried blood spots that are routinely collected from newborns in Denmark, as they are in many other countries in the world, to screen for various metabolic diseases. Is there any big part that you would like to point to?
Well, I think that it's good to know that I used to work in analytical chemistry for many years in toxicology as a resident in the hospital. So I have the clinician perspective on what a reliable analysis is and what patients and clinicians need. Mm-hmm. In that regard. It's a good background in terms of where do I want my research to go.
Mm-hmm. So you have the point of view of the analytical chemist, but also almost the contact with the patients. Or do you work with patients? Or
so I don't anymore, but as a resident, I was analyzing blood and urine and all kinds of stuff to report to different clinical services. This is when you know the impact of what you're doing on someone's life. Yeah, this is not trivial at all. Mm-hmm. And also, I think you get a sense of what is important in the analytical part of things, but also how a test is used.
I think it's a unique perspective as well to have the kind of technical aspect of really knowing how the measurements are done for metabolomics, for example, and also to know in real life how it's applied when you work in the clinics or when in contact with the patients, that you can really see that you can have a quick impact on people's lives if you can make a better diagnosis, for example, because you have better tools.
And I've also seen the impact of bad, like errors, and that can be really dramatic. One thing I enjoyed doing was discovering both basic science in my PhD, but also clinical research. I was working in a clinical research unit in a cancer institute, so I was also very close to actual clinical trials and how do you implement new treatments, etc., and how all the analytical chemistry can come to support this, like so many applications anyway.
And metabolomics, that's also. Is it a big part of it? In my understanding, newborn screening is probably one of the main applications at the moment of metabolomics in the clinics. Huh?
Yeah, I'm not aware of all the applications, obviously, but newborn screening is one that's happening daily.
Can you maybe explain a bit what that is? Because I learned about it as I got deeper into metabolomics, but I'm sure there are some people who don't know exactly what that is.
Yes, every baby born in Denmark, Greenland and Faroe Islands, in our case, because this is where I am, gets... so we collect a dry blood spot 2 to 3 days after birth. We take the heel of the baby and we get a bit of blood and put it on the filter paper. And these filter papers are sent to us, and we check for some rare inborn errors of metabolism, and also other kinds of diseases that are detectable at birth. And so we screen 18 diseases now, as far as I remember, because the number is increasing.
It's different in every country, right? Like everyone has their own way of exploiting that.
Yeah, I think in France, where I was born, they only measure 5 diseases, and of course there are lots of consequences and politics behind it. It's one of the principles in Denmark, at least, is that you should not screen for disease that you cannot cure or treat.
That's an interesting point of view, yeah.
And it's always a debate, because what do you mean by treatment or cure? Like the last study I was working on is a genetic disorders. Of course, you cannot change the genetics of people, but there are supportive therapies that can help people improve their quality of life. So where do you draw the line?
There's also understanding, isn't there? Because it's also, I think, important that, say, if you have a strong phenotype and a strong manifestation of a disease that you don't know you have, I guess it makes a huge difference for the patient to at least put a name on what's happening to them. Exactly. And not just think that they're the odd one in the group.
Yeah, that's exactly the example of my last study that I'm writing right now, and the poster I had at MedSoc 2021. So we can talk about this later.
We'll come back to this, yes.
Yes, but exactly. And so, newborn screening is there for that. And it's, in many countries, it's based on mass spectrometry. Mm-hmm. This is how this metabolomics unit started where I am at the moment. And they wanted to build on this experience that they had on dry blood spot analysis using mass spectrometry to develop more untargeted types of analysis. Of course, the newborn screening, we target a certain number of compounds. We don't do untargeted, obviously. So the idea was, can we learn more from these samples? And also in Denmark, these samples have been stored in the biobank for the last 30-something years. They have this huge gold mine of samples that can be retrieved for research. There is really big potential. I have three different approaches. One is biomarker discovery. The point is exactly how can we add a new disease to that screening that would really make a difference for patients. So find the right set of biomarkers to detect that disease. We also have more mechanistic explorations of, what is this dry blood spot? What are those samples telling us about this disease? Because dry blood spot is usually collected right after birth, but in some other studies, we collect it later in life just because it's a bit less invasive than an actual plasma collection. Yeah. So we use that also sometimes for adults.
Is there a stability question as well, that you want to study similar types of samples? Because if you collect a large liquid sample, maybe the way of preserving it and the way it's stable is different from a small blood sample on a piece of paper.
There are so many methodological questions behind dry blood spot versus plasma. And plasma is much more defined and studied, so it's easier in many ways, but it's just a different type of sample, so you cannot expect to really see the same. Yeah. In dry blood spot, we have not so much data on it, and that's the third approach of my work, methodological studies, where we want to see what these samples can offer. Are they indeed stable through time? Can we see any type of metabolites on them, or are maybe some classes of metabolites are not reliable, or et cetera, et cetera? So we have a lot of data on that we want to process and publish soon. I guess. So that would come out hopefully in the next year. Those three aspects we use metabolomics for. We have to restrict ourselves because it's just so easy to get lost with all the applications possible.
Yeah, I guess. Okay, so let's talk about one of your most recent papers. It's an application of untargeted metabolomics to study autism in newborn screening samples. Kind of paraphrase the title of it. It's published in the Journal of Molecular Neuroscience in 2021. Do you want to give a quick overview of what the paper is about?
Yes, it was my first paper as first author in metabolomics. Even though I have been doing research for many years, metabolomics is a challenging field. You need to know a lot about it before you can publish something that makes sense, I would say. And so this paper was a trial study for me, and I learned so much from it because I made all the mistakes possible. When I say mistakes, I mean mainly in the design, because I'm very happy with the processing considering the data in the end. But this really stresses the importance of having a proper design if you want to do anything.
Did you get to do the design by yourself, or did you start work from samples that were produced by other people before? Because that happens very often.
My manager at the time was the one making the design, and I didn't object to it because I wasn't knowledgeable enough, and we thought this would be good trial, and we both learned from it a lot that this was not optimal. We were aware, for instance, that batch, like, you know, every time you analyze a batch in metabolomics, you have a lot of differences in batch, and instead of just accepting that and thinking, okay, we will do some correction afterwards, which is thought, okay, let's go with one batch, that should be enough. But of course, it's very few samples, and so when you do untargeted metabolomics on 74 samples, it's just too few anyway. So that was our first mistake, sample size, right? And then also
so you think you think you would have been better off having several batches and more replicates or more conditions?
Oh yes. Yeah. But at the same time, our purpose was to test our methods mainly, and I don't think this would have been realistic to try to both answer methodological questions, as in what is the best design for autism research, what is the best method, and at the same time answer the research question itself, as in, can we see biomarkers for autism? And then I think that this is mistakes that we always want to do because we want to answer too many questions at the same time. And so,
but sometimes these are the constraints you have in the research, like you don't have the space or the money to do a preparation study and then to do a full-blown study.
I think in our case, even for the methodological questions, we could have answered them much better. We thought it would be simpler, but it turned out to be a real pain because, you know, garbage in, garbage out. And if you don't design your study properly, you will suffer in the processing. And I think that you need to spend the time doing the design and try to really think of what confounders you will have. And that was the second lesson we had in this paper.
Do you want to talk
just
about
like all these the confounders of dry blood spot, because it's not common to do untargeted metabolomics on dry blood spots. If I have to list, I mean, in the paper it's explained. The one that was very important is age at sampling. So whether you have collected this dry blood spot 2 days after birth or 10 days after birth, or etc. That's extremely important if you want to work on dry blood spot, and also the gestational age of the baby, but that's something that's known already. So it was not a surprise really, but that's something you should take into account in your design and other aspects.
I'm surprised that gender is so small compared to other confounders. Isn't that unusual?
No, it's a repeated finding in the studies I've processed. Gender has never been significantly influencing the metabolome, because at birth boys and girls were more or less the same.
It's interesting. It's really interesting.
Of course, if you have
adults,
blood
it's a very
spots
different
for
picture.
adults, exactly. But at birth it doesn't matter so much. I mean, not that we could see so far.
And
the seasonal effect is very interesting. I think that I was kind of playing around with my data, and I thought, okay, the month of birth is actually very important. And of course, it makes sense that if you're born in winter or in the summer, especially in countries like Denmark, it makes a huge difference. I guess maybe in some other countries it's not so visible, but there is always a yearly cycle. And that's
possibly because of light and things like this. Would you expect it could be different in different countries?
Yeah, I would say that also. You know, I mean, I'm prone to allergies in the spring and summer. In some countries, you will have infections, flu, and you can also, of course, sun exposure, obviously, but also air pollution in cities changes according to seasons. And diet, obviously.
That would be a whole study of its own, yeah. Just
Oh
to
yes,
figure out
but
that
we are exploring those things as well. So yeah, we will have more publications talking about this in the future.
Okay.
I think that even though our design did not allow us to give any strong signal about autism, we learned a lot about dry blood spots, and also what I wanted to see is if my method was appropriate for studying autism. You mentioned one of the table of the article.
I really liked it. Can I explain how I see it? It's an unusual table because it's not actually the results of the paper, right? It's more the results of the literature search based on what was interesting in the results. So it's of publications for analytes that were found to be relevant in autism in at least 3 publications, right? Yes. So then you have the whole output of the literature search at the fingertips of the person who is reading the paper, as you would in a review article, let's say, but in a much nicer way than it's usually presented, because normally you put that in the text and it's all a bit messed up, and you have a list here from that paper and a list here from that paper. And I personally, when I read papers, I like this kind of tables because it makes the work of other people much easier to take and digest and reuse that information. That is a lot of work to put together.
Yes, and I think we all tedious work in our research, and every time I go through that type of work, I'm like, how can I share this? Because it's sad that someone has to do it again. And this is also why I like reviews, but it's very often that reviews are not comprehensive, and I'm not blaming them at all. It's just the way it is, right? The reviewers for that specific paper asked me to remove a lot of references because I had even more. And that's a bit of my weakness as a researcher. I'd like to share all those research I've made in the literature to see, okay, have I really gone around this topic? Because I couldn't see specific biomarkers that were really strongly connected to autism, I thought, what about the other studies? Can I at least reproduce anything or not reproduce? Because
this is a classical thing to do, at least if you don't have anything shiny to show from the results, to check how you compare it with the others, right?
Yeah, and in general, negative results are still results, and I'm sad that that's it's always more complicated to defend. But those many metabolites that had been reported in the literature to be potentially involved in autism, I could not see them in my sample. Of course, it could be because of the type of sample, as we said, the age they were collected, the method, or anything, sample size, indeed. If I'm to use that method for a bigger study, am I going to check these findings again, look at what had been reported, and how do I fit in that picture? That was the point of this table.
Looking back, do you see places where you could have saved time besides the project planning, maybe in the execution of the analysis or the preparation of the paper?
I saved the time by having good acquisition, and that you don't need to just try to clean it afterwards.
Yeah.
That's something, of course, it was time consuming because I didn't get the lucky kind of easy, strong finding that you can just exploit and be happy with. Even if you try to do your pre-processing, peak integration and everything as thoroughly as possible, there's always something that pops in your statistics that don't make sense because the noise features will be there. Randomly, they just ended up being stronger in cases than in controls, and etc. You need to do the tedious work of double checking, and skipping that, it opens the door to wrong conclusions.
There's another tedious work I'm thinking of now, that is how to identify analytes. I know in other data sets you've had to tell metaboanalysts, for example, which of the 400 or 500 metabolites you were looking at, which identifiers they had, so that metaboanalysts would recognize them and then use them for pathway analysis or whatever. And this is also very tedious and, we say in French, ungrateful work.
I think everyone is afraid of that part of the data processing and interpretation that is metabolite annotation, because even though things are progressing very fast, there is always a big risk of misidentification. And all these unknowns, especially if you work with clinicians who don't know what to do with unknowns, and I totally understand, because you cannot go much further with that. If you're more in an explorative type of study where you want to see what your method covers, then maybe it's not so important to be identifying everything, and you can get only a chemical class in the information, for instance, and be happy with that. But when you start trying to use that data to interpret mechanisms as in pathway, which pathway is involved, you have more tools out there, but they're all based on the idea that you know exactly which metabolite you're talking about.
Which sometimes even the method doesn't allow, because I know in mass spec we often measure some signals of things, and then it's that structure more or less, but it can still correspond to many different metabolites that would
isomers,
be identified differently.
I think there is a margin of errors on the side of annotation, but also on the side of those databases for pathway analysis are based on someone's research, right? Or people's research. So they are also full of mistakes, I'm sorry to say, but
also
necessarily
that's
they are.
true. And the pathways often don't cover everything, but the pathways that are the map behind also miss information, and they often don't take in all the analytes we would have to give them also. So there's a whole bunch of analytes that will automatically fall out because they don't map to anything yet.
Yes, and I think that it's really important that when you use those tools, you know the limitations, and you're aware of those limitations and what your method is actually giving you. I mean, because typically when I was using the metaboanalyst pathway analysis and metabolite set enrichment analysis, they depending on which database you choose or exactly how you name your metabolites, then you get actually quite different results. So you have to be careful when reporting your results. Okay, what I got this result, but because I had this list of metabolites, and it's not necessarily the truth. It's just the truth from the angle you've been.
I think studying. Every interpretation is a kind of special juxtaposition of a data set, the tools you use to look at it, and how you identify the data set for the tool, because there's also a translation moment there. And then you look at it from a certain angle that is the one of what you know and what the question you're trying to answer. So it's all different things that kind of narrow down the question to something that is actually very biased in many different ways that add up to what you get at the end. In that context, the bias is necessary, I think, because you have to reduce to something, but you have to remain aware of the bias that you have. And then you can go on, I think, and interpret and make hypotheses or even draw conclusions, as long as you don't forget that you've made these limitations before.
Yeah, and I think that one thing that researchers should accept is that sometimes you have to give up on some analysis because it's just not reliable. Even though you can always run a script, you can always click around and generate results.
Are there hard limits that should not be crossed that you can think of?
A quarter of your metabolites are mapped in databases. Do you believe what you see? Is it reliable? I mean, maybe you will be thrilled because, this pathway, I've seen that in a paper. That makes sense. Let's just stick that. And there is this confirmation bias that comes again and again. And you have to remember that this might not be true. And even if it is, I mean, is it the actual finding that people are interested in? Should people spend time on that finding really, or are we going to move forward with that, or is it just good because then in the paper you can say that's you confirmed that finding? I think that in metabolomics, especially because we usually design studies without a specific hypothesis in the beginning, it is very easy to get into these dilemmas. Okay, I found this, but should I report it or not? And if I don't report it, is it considered hiding something or not? Or if I had one way to express how I consider a study successful, I would say that it's about going further to the next step in a concrete manner. Of course, it depends on your research question, but did I learn something concrete that I can apply? And am I ready to take that next step and do it better next time?
Maybe a good example of this is the poster that you presented at the Metabolomics Society. Do you want to explain quickly what the poster was about and the main finding of it?
Yeah, it's a different story than my first paper. And in that one, it's more of a, I cannot really say success story because it's just the one study and I have no clue if it's going to go anywhere.
I'm sure a lot of people would be happy to get that kind of output.
Yeah, I was a bit surprised myself that no one had found it before, but let's go back to the research question.
It's about a different disease, right?
Yeah, it's about 22q11 deletion syndrome, which is the most common deletion syndrome. People are born and they're missing a big chunk of their chromosome 11. They're missing many genes. And the thing is, it's not lethal. You might actually die because there are like congenital heart defects, etc. But a lot of people survive and they have various phenotypes and many different organs are involved. Because a lot of the manifestations are quite unspecific, it takes several years before people get the proper diagnosis. And that's why we're fighting here, because we think that these people should be diagnosed at birth, but they have to go through many years seeing different experts, and sometimes they never get diagnosed. They have kids who they carry on that deletion, and I think it's sad that they weren't informed because it's possible to do so. And of course, genetic analysis of everyone that is born is just not yet possible, I would say, and also maybe not wishable. I mean, that's another debate, but if we could,
the newborn screening is happening, so we could exploit that. I guess it's the main idea.
Exactly. Since we are anyway collecting those dried blood spots, I mean, maybe there is something in those dried blood spots that could help us detect that deletion. In the literature, I was quite surprised. A lot of people are really focused on the genetic aspects of it, like which is the deletion big or short, or which genes are involved. But doing just metabolomics on the blood to see what happens in the blood in the end has not been done much. And I could not find anywhere someone that had reported the tyrosine level, for instance. It is at lower levels in cases compared to controls at birth. And the proline is in contrast in higher levels in cases than in controls. And that has been shown in the past because the proline dehydrogenase gene is deleted. So that made sense. The proline was kind of a finding that I could expect, but not the tyrosine. And the good part of these two amino acids is that they are both part of newborn screening in many, many places. So it's not anything new. You don't ask the labs to develop a new method. You just ask them to take that data, make a ratio, and we need to do more studies to see which threshold should be used for that ratio.
And I guess it could be used as a pointer, even if the significance is not enough to really discriminate from other diseases, that at least you might be tempted to then do a genetic test.
For every screening, we always have a second analysis to confirm the diagnosis. And in the case of the 22q11 deletion syndrome, we would need the genetic analysis for sure to confirm. But the idea is, can we detect some people that probably have this deletion syndrome? And
how did the idea come
early,
to make a ratio of those two metabolites?
I'm not aware of all the ratio used in clinics, but I know that some are used already in newborn screening. And so it was already something that I was thinking of. And I was very happy to see that the MetaboAnalyst biomarker discovery type of analysis computes the ratios for you. So you don't need to bother doing it yourself. It computes the ratios and it treats them as variables like other metabolites, and it will select the 20 best ratios. And this is how this one popped, actually.
Okay.
And then it made sense because most of the metabolites significantly different in cases than in controls are have lower levels, but proline is one of the few that have higher levels. So of course, if you make a ratio, then you will amplify the effect. So ratios are very helpful for that, and it's very simple. I'm very happy to think that this can be implemented in many places if they want to, obviously. Because again, this deletion syndrome cannot be cured, as we mentioned earlier. So some states will not want to screen for that. But that's another discussion.
Mm-hmm. So let's move towards more general topics about data interpretation. Is there something that, in your experience, that you find particularly challenging for the interpretation itself?
If I was to list some things that I think people should be aware of, is like, well, there is also the lack of interpretation. So that's the first thing. If you stop at the descriptive analysis of your data, I think it's a bit sad, because if you don't do that job, then who is going to do it? It's a bit sad that many papers don't bother going further than that. And
why do you think that is?
Obviously, it's a lot of work. And you really need a lot of knowledge. One person can not be expert everywhere, right? So if you don't sort of contract your PhD or whatever, and you don't have the time to go further, and you just get that paper out, I'm not blaming anyone for doing this. This doesn't satisfy me anyway, personally.
Yes, I know that feeling.
I know. And also it's very easy when you do descriptive, fall again into this confirmation bias that, oh yeah, well, this other study found this as well, and so that's right, and this is it. And I think that it's only when you try to go further that you see if it makes sense and if it's actually going to be useful to the community. So
how do you go further? What are the tools that you use? Recently, I posted a poll on LinkedIn to ask people how they do metabolomics interpretation. And one of the options I gave them was pen, paper, and PubMed.
Yeah, that's the tedious, painful way.
Yeah.
It depends on your approach. If you're doing biomarker discovery, you might have some findings where you see biomarkers that can help detecting whatever disease you want to detect. But I think that so there is the interpretation. Do they make sense in terms of mechanism? And sometimes you don't know, right? And then of course it's not much you can do except really digging into literature and all the tools and the databases. And I think the databases are like pathway analysis and stuff like that. If you really want to go deep into why these biomarkers have changed, you can go there, but again, with the limitations we mentioned. And sometimes it's not necessary to know why they're like this. If your goal is just to find a biomarker, maybe you just need to check if people can measure it. Is it stable in your samples? And so then you go more for kind of the methodological, logistic kind of questions.
If you study a disease that's not well studied, then you can maybe always have the kind of exit strategy to say, well, there isn't much information about mechanisms yet, so I'm putting this out there, and then maybe one day someone else can put it together with something else to figure out. There are cases like this.
Yeah, and I think that sharing raw data is just also the way forward for that, because it happened to me, typically for the 22q11 deletion syndrome, that there were 1 or 2 studies with its measurements, but they would not share the full list of metabolites they had measured. So they reported only the positive results, and that's it's too bad.
So entire data sets that are all expressed in relative values, so let's say relative to control. And then it's all there, like it's like hundreds of rows of things. They're like, yeah, but what does it mean? Because I just want to see what it's like in the controls or what it's like in the case, but not this ratio thing. And you don't have access to it. And this really is a pity.
If I want to go back to what can go wrong in interpretation, I would say that one of the obvious, maybe it's bad design, bad acquisition, bad processing, and bad statistics are kind of the big pitfalls. And it's not always easy to know whether your method is adapted. So you definitely need to talk to other people, read a lot, and look at webinars and courses, and try to get as many opinions as you can, just to kind of make your own opinion about what is adapted for your type of data. I think you cannot alone just necessarily figure out what's best unless you have a lot of experience already. But yeah, as a beginner, it's just impossible. But the risk with these, if you have a bad design, you might not, and you might see something, but maybe it's just totally unreliable artifacts. And then that's the same for bad stats, etc. I mean, you always need to be aware of your bias and confounders. It's very sample specific, matrix specific. Like you have to understand what you are looking at. Is it blood from adults? Is it blood from newborns? Are these people taking medications, a diet, and this and that? And
would you say that you should always keep in mind why you're doing this experiment as well? Because I know in my experience, there are also pitfalls that just fall on the road as you go. And I think this applies to any type of experiment also in this case.
And I think that's a big mistake that my unit has made a bit in the past, as in, initially, I was supposed to just acquire data and deliver data to other people who were supposed to analyze them. But these people were not metabolomics experts. And, they were a bit too optimistic as in, oh, yeah, we'll figure things out. But you cannot just figure things out of nowhere. It takes a lot of time and knowledge about what is mass spectrometry in my case. What do you see? Those adducts, where do they come from? Can you pull them together? What is this noise? I'm not even talking about annotation, but what is intensity? What is peak integration?
And I guess in this context, it really helps also to have people either more experienced or at least in a similar situation that you can work with. Did you have this kind of environment, or did you have to go actively look for help on the outside?
Well, initially I was alone, so I was really looking for help, and this is also how I ended up creating the Danish Clinical Metabolomics Network, because I really needed to gather people and
this is what networks are for, yeah.
Yeah, exactly. And I was like, okay, I'm alone, I can't do this, and I just need people to talk to each other. And I learned a lot from these people. And also, of course, after some point in my unit, we recruited a bioinformatician, and she had a lot of experience with her own workflow. And so we kind of adopted that workflow as a default one, which had a lot of good innovations. I couldn't have done this by myself. Even though I think that it's more and more feasible with videos and tutorials online to find your way, but you need an understanding, as you say, of what you're looking for, what is your goal, and what is the data you're working with. So it doesn't come in a day, right?
Absolutely, it really takes time. Yeah,
and I think that we cannot avoid the pilot studies. People don't want pilot studies. They want good, nice studies, well designed, but you cannot design something if you don't know what your samples are bringing to you and what your confounders are, etc. So you need to go through that. And jumping steps never helps, if you ask me. I don't think that sample size can always compensate for bad design. And it's not everyone that can afford to have big sample size anyway.
Of course.
To go back to these pitfalls, of course, it's very difficult to know if your stats and your processing is reliable, but I would not trust only the reviewers of your paper. I would try to have someone look at it before.
Yes.
Because reviewers, they have also their own limited time and their own vision of things.
Have you also been disappointed in your reviewers? Because I have.
Yeah. Oh, yes. I've had reviewers that had really good points and were really constructive, and I had all kinds of reviewers, of course. But you have to remember, reviewers are human beings, right? So the day they read your paper, they might not be in the right mood.
Of course.
And if they haven't understood something, maybe it's just you weren't clear enough because you have the nose in your paper, right? I think that it's a very big part of interpretation. It's what do you report and how do you report that interpretation? How do you translate what you have found into something that people can understand and use? And that's even, I would say, the next step after interpretation is reporting. It's not trivial either at all, actually. It really depends on your audience, right?
Yeah, and in a scientific paper, is it a sort of storytelling, you would say, or would you put it differently? Because, for example, when you explain now the story back to your poster about the proline tyrosine ratio and how the proline dehydrogenase is missing from those missing genes and stuff, for me, that's the beginning of a story. That's how you help make the information stick in other people's brains because the facts are kind of following. How do you do this reporting in scientific publications?
It really depends on your goal. I think it's much easier in cases such as my last study where I indeed found something and it made sense. And so
that helps. Yes.
It was just beautiful to write that paper because literature made sense and my results made sense. And I have this feeling I'm bringing something. It's just sad that the data has been sitting for 3 years before anyone looked at it because it was so difficult in the end for someone else to figure out what to do with that. So again, I think we should have saved time there
but I think there's really also a gold mine in studies that are sitting on someone's hard drive and should be exploited.
And we have
but it's really a lot of work, for sure.
It is a lot of work, and so the storytelling sometimes is very easy. Easy, I don't know, it's never easy. You just still do need
flows,
to, you need to go to in the literature and take it. I usually take like so many notes, and of course very little gets into the paper, only the essence of it. And I'm trying to keep that red line, indeed, the story. It's much more difficult when you do explorative type of studies, because then you're like, okay, I got so many things to see, but what do I want to present? So you have to take a decision and choose some examples, and you go for examples, and you just assume people will dig if they want to. But how do you choose those examples? Then I guess it's really personal.
There's a big subjective part in a lot of the discussion of papers.
Yeah, and again, one of the big pitfalls is jumping to conclusions, and just because the literature you've been the first search has gotten whatever result, I think that the skill of interpretation cannot be developed or expanded if you don't have the skill for criticizing literature and doing a proper literature search and doing this detective work of actually reading the papers you cite. I'm sorry, because it's so easy to cite a paper based on one statement in the abstract, and you don't read it, and you propagate findings that might not be true. And I think you can't avoid it sometimes, but some signals are just amplified in the literature in a non-constructive manner. So it's also part of the tedious work, and our duty as a romantic of science, I think it's our duty to check these findings and see, okay, can I actually cite that paper, and does it make sense to cite that example in my data? Is it going to bring something to others? Yeah.
Would you say then that this critical thinking would be the most important skill for you?
Yeah. Having a bit of marketing skill is definitely important in science, but the more you know, you don't know, right? So as a pharmacist, I've been educated on various diseases and various organs, etc. And we cannot have a comprehensive view of what's happening in a human's body. And this is why it's so important to collaborate with other experts. Never think that your vision is just the only vision. Also, having a critical mind, for me, goes together with opening yourself to others' opinions and chasing them, because when you go to conferences, it's very easy to just listen and never interact. But I think that I've learned so much from just going there and saying, oh, I found this. What do you think about this? And then sometimes you get extremely interesting conversations that didn't expect, really. And
but it all begins, as in any human interaction, I think it all begins with this moment where you make yourself vulnerable by saying, this is my work and this is what I found. Do you say it's good or do you say it's bad? And we can always discuss whatever your answer is, but you're exposing yourself, and this is why it's of course much more comfortable to sit at the back of the audience and say nothing, but you don't get as much as if you ask a question or you actually present your poster to people or talk at the conference.
Yeah, and I think that I'm a very social person, so I enjoy that type of interaction. I understand it's not the same for everyone, but if it's not your strong suit, like ask your close collaborator who knows about the study to do it for you, maybe. And you have to get out there with that story and challenge it. And is it robust? Because again, one statistical analysis is not the truth. And that's something I tried to do in my last study, that I was trying to see if these biomarkers were the ones, like the one that would find, can I find them through 3, 4, 5 different type of tools and analysis. You can of course take one and report it, but you have to challenge that, right, and reproduce.
How did that work out? Did you get?
Oh, it went well actually.
Yeah.
And this is why I was happy with the findings, because.
Which tools did you use actually? What are the tools that you use in your work?
Classical ones. I'm not. How do you say? I'm not a bioinformatician. I'm not making all my own R packages and stuff. But I get inspired by other papers and then webinars, and like very recently, I wrote to Julien Bocard, who's been teaching at a workshop at the METSOT 2021. And because he was showing a very nice plot on how the most interesting biomarkers or metabolites were impacting the different factors in his studies. You have to think of your samples, so many dimensions, right? Let's say you have a case control study, you have people with diabetes, people without diabetes, but these people also have different age, different comorbidities, different gender, different this and that. And all these factors, I think it's very important to look at them and not ignore them. It's not because you're interested only in diabetes that you should ignore these ones. There are now different type of analysis, statistical analysis that you can use to see, is my diabetic condition actually the most dominant one in the story, or is it totally
or am I studying something else?
Yeah, because sometimes you just have the nose on your diabetes and you forget that maybe obesity is totally what is triggering. I don't know. But of course, the more you amplify the numbers of factors, the more you open the door to random findings as well. It depends on your sample size. So you have to be very careful with that. And of course, it's very fun to put every factor you can in your table. But there again, you have to draw a line where what's relevant or not. But
this is also advice I give if you have different types of data, that to keep all the factors that you know in your data set as long as possible, to not just get rid of the columns you don't need, because
exactly
nobody cares if you smoke or not, but we might, once we reduce the groups to this and that, and then realize all the smokers are left and all the non-smokers are right, or things like this. Yeah.
And this is also how you go for handling outliers. So I usually do the Permanova in terms of tools you were asking. The Permanova is we're sharing the scripts always when we publish. It's interesting because it shows all the factors that you're testing, or I also call them metadata variables, so age and sex and all these ones. You can see to what extent they impact the metabolome and if these effect is significant or not. So you get two type of information here, the extent and the significance. And then the thing that Julien was showing the other day, I thought was very interesting, is that once you have already some candidate biomarker, let's say, or like 20 most interesting metabolites in your whole data set, how do you know why they are what they are? What influences them the most? And he had this plot where you could test the importance of each of the factors, so the metadata variables for each of these biomarkers, and you could have this plot where you add the effects on top of one another. I mean, it's very visual, it's very easy to see, oh, okay, so actually that's a big biomarker that has super strong effect. Well, it's mainly driven by age, or it's mainly driven by sex. And it was very interesting, and it comes together with the Permanova. I'm a quite excited to use it in my next study, I guess.
Yeah, imagine.
Even though it's been actually published some years ago, but somehow I never came across it before now. So yeah.
Do you feel it helps when the visuals are good for a new way to analyze? It does help, doesn't it?
I mean, this is fundamental. You cannot having a good interpretation and being unable to report it properly. It's not constructive, and you fail again. Even if you have the right interpretation, if you cannot report your results in a way that people can use it or understand it themselves, then it doesn't work. I think it's a lot about writing publications and making the correct plots, and it doesn't come naturally. I was terrible in my first paper writing, but I think I'm much better now. I hope so anyway.
It takes practice for sure.
It takes practice, and also it takes reading again and then showing your results to others, and
showing it to others, because you can write 20 papers. If you never show them to anyone, you're probably not learning as much as if you show it first to the people you work with, and then to collaborators, then to reviewers, and present them at conferences. It really makes a big difference.
The outsider eye is important, and I think that it's exposing yourself. And this red line, you have to really put yourself in the shoes of someone who has no clue what you're talking about.
Yeah, and leveled with the audience. Yeah,
that's not easy, but that's something you have to practice.
That's the story I'm talking about. It's the red line that is helping you to go, also including the study design and including all the steps to go and take the reader in, because it is a reader for a paper, along the story to the conclusion that you have. And of course, the better the conclusion, the more exciting it is, and the easier it is probably to keep them interested as well. Now, as we're approaching the end of our episode today, would you like to share with the listeners what your process is to interpret metabolomic data?
I have a usual flow I'm following when I interpret data. I think that it helps sometimes not forgetting big parts of things. So the first is, of course, the technical quality of the data. And I think that we should not overlook this, because if you overlook this, you will definitely interpret something, but you might just report false findings, and that would be sad. Be very aware of what is a good acquisition, what is a good data. Ask for help if you don't know how to assess this. There might be some post-acquisition corrections you can do, and there are many things, and I've done some, so it's totally possible. It doesn't mean that you can always rely on the data afterwards, but some things can be corrected. A second part would be to check roughly if your studied condition, I'm here in an example of a case control study, is your studied condition significantly visible or not? If it's a no, then can you explain, do you have strong confounders? Is there too much noise? Can you go back to the technical quality step and improve it and try again? Or do you have to just improve your design and make a new study? At the end, even if nothing is possible, you will always learn something from that. It's always positive, even if disappointing. In the case of a positive, significant effect of your studied condition, then you have to look at the strengths of that effect and in comparison to other factors, as we said. And you can learn from that to improve the methods and your design for the next study. And then my next step is to look at metabolites, which of those have actually an impact, which are interesting. And depending on your goal, then you have different approach. If it's for biomarker discovery, explaining them is of course interesting, but if you cannot explain them, it's not the end of the world. What you need for a good biomarker is something that's specific, that is sensitive, and is robust. If you apply that analysis in real life setting with different type of samples, etc., and can you acquire them with various methods, or is it difficult to acquire it, etc.? So these are the questions I would address in terms of biomarker discovery. And then for mechanistic exploration, if I have a study more on mechanistic exploration, I look at patterns and what literature says, but be careful with the confirmation bias again.
Yeah.
And if you do pathway analysis or cross-omics, you have to understand the tools you're using. Collaboration is a key here. And remember that the method you use has limitation. And so that's it for the mechanistic exploration. And also, then the last step is how do you report these findings, right? And I don't have an actual guideline for that. I think
this is the whole reason for this, because there is no guideline. I think it really helps when we discuss this with you and with other people to get at least a feeling for how people do it. That's even for the people who are a bit shy at the conference and don't dare to ask questions, that they also get this input and these ideas, and maybe also go and ask next time that's they're in the conference room, that they dare to ask questions. What do you find the most promising for applications of metabolomics?
I think the main idea for me in terms of application of metabolomics is the question, am I going to make a difference for the patients? And if yes, in a realistic time frame, like is it going to be in 30 years or is it going to be in 5 years? And I think that is very tempting with metabolomics. There is so much potential that you easily get lost in exploration. And the clinician in me is always trying to keep track on the idea, are we going to get there to this application?
I feel it's like a positive pressure for you that this presence of the patients help you to work better in that field.
It gives a lot of meaning because I know what... I know the application of biochemical analysis in the real world, and I know what we don't. I don't know what we don't have, but I know we don't have a lot of things, and we're missing a lot. And I also know that when you get a result, even personally in my family or from myself, when I get a number on a paper saying, "Oh, you get that level of this, and this means that," I'm always thinking, really? Who knows? Of course, I want to trust that most labs are doing a good job, but you have to keep in mind that everything that you go through as a patient yourself has been developed based on research, and researchers are human beings, and of course things are usually not implemented in the clinic if they're not reproduced and double checked X times.
There's the methodology that can be faulty, but there's also the entire story behind it that can be faulty because of
and sometimes it takes
believing that it's a one way and it's actually something else, and this we find out much later.
Sometimes it takes decades before you find out that this biomarker was actually not specific enough, and this has triggered so much damage, and you cannot know that, of course, beforehand. But that's something to keep in mind.
Yeah, you as long as it remains like a positive pressure to do good work and not a daunting fear that you might make a mistake, right?
Exactly. I think you have to find a good balance between, I want this to be applied in the clinic as fast as possible, but this has to be reliable as well. Like any researcher, we have that pressure of publishing and of applying for grants and paying for our own salaries. And in my case, it's a short-term contract, and I will not be at SSI next year, and I will work for something else. So you have to keep your integrity through all these pressures. Remember why you're doing it, right? This is maybe why I'm described as a romantic of science. I'm trying to keep...
Self-described or other people described?
My companion says that because he thinks that I don't know. It's I want to believe that most of the people are like me anyway, that they really want to do a good job and they don't only chase p-values. But there are also some that would not maybe be so careful, I would say. Not necessarily because they are consciously doing it, but it's a lot of knowledge, so it's very difficult.
Julie, thank you very much for taking part in this podcast and for speaking with me. If people want to contact you, then they can contact you directly.
Yes, great. If anyone wants to write to me, they're very welcome. So
that's really nice.
If anything is not clear, don't hesitate to poke me. My LinkedIn, because LinkedIn is a bit more sustainable. Yeah, thank you so much again for letting me speak.
I found it very, very interesting. Thank you for joining us in this discussion. I hope that this episode gave you new insights and ideas on how to plan, conduct, and communicate your own metabolomics projects. If you'd like to continue this journey with us, make sure to register for the Metabolomist email list on the podcast webpage. For regular news on metabolomics and data interpretation, you can connect with me, Alice Limonciel, on LinkedIn, where I post on metabolites, analysis strategies, data processing tools, and more. And make sure to check out our other podcast episodes on the Metabolomist website.